Good morning, students. So, the last class we discussed some problems based on the blocks connected by the strings. And so now let us see some more problems based on that, simple problems based on that Newton's laws here. And so now first I am discussing some models based on the string having some mass. So in the last class we discussed only that massless strings here. And so now in today's class let us see that strings having some mass. How to solve the problems based on the strings having some mass. And so for this I am taking this a block of mass m is placed on a horizontal surface here. Now it is pulled with a rope having some mass m, right? So it is pulled with a rope having some mass m. So by applying a force F here, the mass of this is m. So now our question is find the force exerted by the rope on the block. So write that problem. A block of mass m is placed on a smooth horizontal surface. A block of mass m, capital M, is placed on a smooth horizontal surface and it is pulled by using a rope. It is pulled by using a rope having mass m, small m, by applying a force F at the free end of the rope. At the free end of the rope. Find the force exerted by the rope on the block. Find the rope exerted by the find the force exerted by the rope on the block. So now let us see this problem. So as we discussed in our previous classes, like the net acceleration of the system directly you can write here. So the net acceleration of the system I can write here as, so this acceleration is nothing but net pulling force by total mass in motion we need to write. So that gives us net acceleration of the system. So I can write here as the applied force is F only. In horizontal direction the only force is F for that entire system. But the mass in motion is m plus m you can write. Because that block is moving as well as that rope is also moving here. And so that the total mass in motion will be m plus m we need to write. And now that is the acceleration of the system. Once if you know the acceleration of the system, you can write that easily. The force with which that rope is pulling that block. So you may consider the free body diagram of either block you may consider, or you can consider the free body diagram of the rope also you can consider. I am taking the free body diagram of this block here. So that FBD of block. So then if you are taking this FBD of this block, then this is capital M. Suppose it is applying some tension at this point as some T here, right? That rope is applying some tension T at that point there. And so now it is moving, it is accelerating with acceleration A, right? And so that in only in horizontal direction on this block, only the T is the acceleration of this block here. T is a force acting on this block which is producing this acceleration here. And so that I can write this equation as this T is equal to m into a you can write, because the only accelerating force is T only. And therefore I can write this as T is equal to m into that a value you can write this as F by m plus m. Now simply that is nothing but the force exerted by this string on the block here. Force exerted by the string on the block. So you may consider this in by taking the free body diagram of this rope also may consider there. By taking the free body diagram of the rope also you can draw this calculation here. If you are taking the free body diagram of this rope here, then this is force F will be there and tension T is there like this. The same tension, the reaction force will be there in backward direction, and so now it is accelerating like this. And so now we need to write the force equation as T minus F is equal to small m into A, because its mass is small m we need to consider here. And then from this we can write this T expression there. T is equal to F minus m into A by that means m into A, that A value is nothing but F by m plus m you can write here. And from this you can calculate this tension. F into m by m plus m you can write here. So right, either you can consider this free body diagram of this block, or you can consider the free body diagram of the rope. You will get the same answer. Now here how now this tension is, we know when the mass is there for the mass is considered for the string, the difference we know when the string is massless and when the string is having that mass, the difference is the tension in the string is different at different points of the string here. Now here how to conclude that tension is different at different points here. Now we can observe that if you are pulling this end of the rope with the force F, if the string is massless, then same force will act here, right? In the same case, if I consider this string is a massless string, then the acceleration of the system will be F by m you will get. F by m is the acceleration, means then this force acting on this block should be F only, right? And so the same force will F will act here. If the string is massless at any point in that string, that length will be, that force will be equal to F only. But whereas when it is having that mass, here if you are applying a force F, then here the force is not equal to F. That force is nothing but m into F by m plus m. Even if you consider at some different points of the string, you will get the different tensions there. That means the tension is different at the different points of the string here, right? And now let us take a tension calculation here to get more clarity regarding this. Let us take one more problem here. So just to only consider this rope here. So a rope of mass m is, just mention it as a uniform rope or uniform string. So uniform string is placed on a smooth horizontal surface, uniform string of length L. Let us include this length L. A uniform string of length L is placed on a smooth horizontal surface. It is pulled by applying a horizontal force F. It is pulled by applying a horizontal force F. Then find tension in the string at a distance x from the free end of the string. At a distance x from the free end of the string, right? So that means now we need to calculate this tension at a distance x from the free end of the string here. So let us say this is the x length. So at this point we need to find this tension in that string. This type of calculation, remember this type of calculation again you will get in the topic chapter called elasticity. In elasticity also we need to calculate the tension at some intermediate points of the string. And so now here actually the mass of the string, so nothing is given, just the word uniform string. So whenever you are finding such a word uniform string, remember that it is having mass. So that means uniform string in the sense it is having mass, that mass is distributed uniformly to over its length. So that means at any element, the element's mass is identical elements of the string if you are taking, it is having that same mass. So that means uniform string means that is the meaning here. It is having mass and then it is that mass is distributed uniformly, right? And so now here as the mass is not given here, I am taking that mass per unit length, linear density, that is called actually linear density, mass per unit length. Or let us assume that as a m as a total mass here. So let m be the total mass of string. So I am assuming this as m be the total mass of the string, right? And so when the total mass of the string is m, now we can write the acceleration of the string here. So that means now it is accelerating here because we are pulling with it a force F. The acceleration of the string we can write it as F by m, right? So that is the acceleration of that string. And now to get the tension at this point here, let us take only the free body diagram of that part here. Suppose I am taking that as A, B, C, right? So then let us take the free body diagram of AB. Again here you may take the free body diagram of AB, or you may consider the free body diagram of BC also may consider here. As I explained in the previous problem, you will get the same answers here. So whenever you are taking that free body diagram of the last elements or the last objects, then calculation will be easy for us. You can observe that here when you are taking the free body diagram of last term, we are getting only directly T expression. And whereas when you are taking this this object, the front part, then we are getting an equation and you need to solve that equation. That is a simplicity when you are taking this last object there. So that I am taking this FBD of AB I am taking here, the FBD of AB. So if you are taking this FBD of AB, the only force acting on this will be tension only, right? So there will be some tension acting on this. I will draw the free body diagram of BC also, then you will get the clarity about that. So this is our AB part here. So if I consider this actually BC part, so this force F is applied here, and then here this tension will be there like this. So then this is accelerating with an acceleration A. So that means if you are taking this BC part, the free body diagram of this BC part will be like this. In the tension, when we introduced the tension in the beginning of this Newton's class or in the first class of second class of that NLM, I explained about this tension. If you are cutting the string here, how to take at the intermediate points of the string. So that means if you are taking this part, then it will pull like this. The tension will pull like this. And if you are taking this part of this free body diagram, then the tension will be in backward direction there like this. So just it is a pulling force. The tension is a pulling force, and tension in the string at the both ends of the string will be opposite in direction. So our required free body diagram is now this one, what we are taking here. So now for this AB, the only force is tension and it is accelerating with acceleration A. And now suppose I am taking this mass of this part as M. I am assuming this mass as M. And so now let us write the force equation for this. So the force equation for this I can write here as T is equal to MA. Now how to write this mass of that string here? So that is the importance of uniform mass here. So this mass capital M is distributed uniformly over its length. When it is distributed uniformly over its length, then you can consider that mass per unit length is a constant. Mass per unit length means, say for example, I am taking an example like I am taking this 100 centimeters rope, and mass of this 100 centimeters rope is 200 grams for example. If I am taking a rope here, the mass of 100 centimeters length is 200 grams. Now if I can, that is uniformly distributed, let us consider here. Now I am taking this 1 centimeter, the mass of 1 centimeter if I consider, that we called mass per unit length or linear density. Linear density means mass per unit length. And so then this value will be 200 by total mass by total length I am writing here. So which is 2 grams per centimeter, right? So that means now it is called linear density. The meaning of that is, if you are taking a length of 1 centimeter string, then its mass is 2 grams. Now if you are taking a string of 10 centimeters, 10 centimeters length if you are taking, then its mass can be written as 10 into 2. The mass of this 10 centimeters can be written as lambda into 10 we can write. That is nothing but 2 into 10. So you will get 20 grams. So that means 1 centimeter is 2 grams means then 10 centimeters will be 2. So mass per unit length into length of the part which we are considering we need to write here to get this M value. And so that I can write, I am substituting that value here. Therefore this T is equal to this M value we are writing as mass per unit length into length of this part here. Length of this part is nothing but X. And this A value is nothing but F by M. So therefore this is F into X by L or F by L into X you can write here. So that is a tension equation there. The tension at a distance of X from this free end of the rope. So only here you need to observe here carefully about this mass here. So this is like lambda mass per unit length into length of the portion which we are writing here. So we are writing the mass of this X centimeters here. So mass per unit length into X centimeters we are writing, and this acceleration is nothing but F by M. So just we are substituting that F by M value here. And so then by simplifying this equation you will get this expression as F by L is F by L into X. So it is the expression for this tension when you are measuring it from free end. So then you will get the graph like if you are, sometimes they may ask about the graph also. If you are taking the graph between this tension versus X, then you will get the graph like this. So T versus that length of this. And so then this graph is nothing but you can write this expression as by using this you can write here. That means it is nothing but y is equal to mx form. So y is equal to mx form here, and so that then this graph will be a straight line passing through this center, passing through this origin here, and the slope of this line we can write this as f by l. So f by l is nothing but the slope. So now solve the same question by taking x from this end. I solve the x from taking from the back end, free end. Now take the x from this end, force applied end, force end, and then write the same expression for the tension. You will get the different expression. And here you can verify whether this expression is correct or wrong. You can verify here. So at x is equal to 0, the tension is 0 we are getting. X is equal to 0 means where it is? The free end of the string. So remember this, at the free end, if you are applying force at this, and if no object is connected like that, then here the tension will be 0. Because here there is no need of pulling any other mass here. Whereas if you are considering here, the tension at this point has to pull this block here. So that definitely some tension must be there at that point. But here behind this point, no mass is there. So that means no need of pulling any mass, and so that the tension at that point will be 0. But whereas that means now whereas if we substitute this x is equal to L, x is equal to L means we will be at this end. So x is equal to L, if you substitute here, then you will get this T is equal to F you will get, which is nothing but the applied force here. So we can verify like this. That means at x is equal to 0, tension will be equal to 0. This is nothing but tension at A, free end. And at x is equal to L if I consider, then tension at this point C will be equal to F, which is the applied force there. So those are the limits for that variation here. That means this line will be, you can represent like this. And at x is equal to L if you consider here, then corresponding tension will be equal to this force. So that is the limits for that. Now similarly, now you solve the problem by taking the x from this free end. So I will say that problem. So write that problem. In the above problem, find the expression for tension. The expression for tension at a distance x from the end. At a distance x from the end, from the end where force is applied. X from the end where force is applied. So derive that expression there for the same thing. Next here I can say another example, like sometimes they may ask to say when the tension is different at different points. We can discuss one more example here. Like I am taking a string is suspended like this. A string having some mass m is suspended like this. Then let us try to write the tension at the different points here. Tension at different points, or let us write tension at a distance x from this free end. So x from this end here. Right? So tension at this point, let us write here. So write that, note down that problem. A uniform string of length L and mass m. A uniform string of length L and mass m is suspended from the ceiling. Find the expression for tension in the string at a distance x from the free end. Free end means now this bottom end here, x from the free end. So now again just to take the free body diagram of this part here, that free end part I am taking here. So that means now again I am taking this as A, B, C. So now I am taking this FBD of AB. So if you are taking this FBD of AB, the forces acting on this, or this is our B here and this is A. So here tension will be there in this direction. and now this weight of the rope will be there in downward direction here. I am taking it as small m. The mass of this part is, I am assuming it as small m here, right? The mass of that part is small m I am assuming, so that its weight will be there in downward direction here, right? And so now the system is now at rest. This total rope is at rest. It is not either moving in upward direction or in downward direction. I can say that it is in equilibrium. So when it is in equilibrium, then you can write this tension T is equal to mg, we can write here. This tension T is equal to mg. And now this can be written as this tension T is equal to m, means same as that of our previous problem. Like mass per unit length into length of this part we need to write here. So mass per unit length is m by L and length of this part is x. Length of this part is x and into g. And therefore this tension we can write this as mg into x by L we can write here. So that is the tension at any point in this string, where x is measured from the bottom of the string here. So now from this you can observe that now tension is different at different points of the string here, right? So tension is different at different points. So tension at the lowest point is 0. So tension at this point, when x is equal to 0, tension at this point is 0. And tension at this highest point is maximum. Total weight is to be supported at this point only. And so tension at point C will be equal to the total weight of this rope here. That means I can write this as at A, that is x is equal to 0. So tension at A is equal to 0. And at C, if I want to write here, so that is x is equal to L, the total length of this rope here, and so that the tension at this point C will be equal to the total, you can substitute here, mg into L by L, and therefore tension at this point C will be equal to mg, you will get maximum tension will be there at this highest point there. So this will be the maximum tension and this is the least tension in that string. So like that we can say that tension will be different at different points in that string. And whereas if you are assuming it is a massless, if the mass of this string is negligible, then no tension will be there at any point there. If otherwise, if any block is suspended, then weight of that block will be equal to weight tension in the string at any point there, right? So it is in case of suspended string. Now let us take another example, like a string is suspended like this. So a string is, I am taking like a string is having some mass m, is suspended like this. Sometimes they will give it as a chain or a string. So it is suspended like this, such that this ends makes an angle theta here. This angle is theta I am taking here. This angle is theta I am taking here. Right? That means the tangent drawn at this point is making an angle theta. So that means now suppose say this is the point A I am taking and this is the point B, and this is the midpoint of the lowest point is C I am taking here, and its mass is suppose say m. M is the mass of this part, and your length is not required here. If you want, you may take it as L. L is the length of that part. So now write that problem. A uniform chain of mass m and length L is connected at two fixed points A and B, is connected at the two fixed points A and B as shown in figure. Then find tension in the string at the point A and at the point C. Find tension in the string at the point A and at the point C. Right? And so now let us see this calculation here. First let us calculate at the point A and B. That means A and B both have same tensions. And so now let us calculate here. So I am taking this rope like this. And so now according to the given information that theta is, suppose here this tension is TA, let us consider here, or T let us consider, and this tension is also then T will be there. here the given information is it is making an angle theta with this vertical. So now you can observe that the tension what we are taking is along the tangential direction only, tangential to the string, and just it is a pulling force. So tension at this point will be along this direction, and tension at this point will be along this direction. And now how to say that tensions are equal in magnitude means you may take like T1 and T2 values you may consider there, for example. Now if you resolve this into components along horizontal direction, if you resolve the tension into components along this direction, for example, if you are taking it as T2 sin theta you will get, and here you will get T1 sin theta you will get, and in horizontal direction that system is at rest and no other force are acting in horizontal direction. So those two must be same. So T1 sin theta is equal to T2 sin theta, or from that you can say that T1 is equal to T2, right? So that's why the tensions are same at the both ends there. So that I am taking directly to avoid that unnecessary calculation, directly you can say that tensions will be T1 T. And so now in addition to that, the other force acting on the string will be weight of the string. So that weight of the string is acting in downward direction here. So this weight of the string is acting like this. So the weight of the string is acting in downward direction. Now let us resolve this tension into components and let us balance this. So this component is T cos theta, and this is T sin theta, and similarly this is T cos theta and T sin theta. So as I said, these components will balance with each other. So in a horizontal direction it is already in equilibrium. Now let us write in vertical direction here. So in vertical direction what we can write is 2T cos theta is equal to mg we can write. And therefore this is nothing but from this you can write this tension is nothing but so therefore this is the tension at either A or tension at either B. So that value will be same, and so that is equal to mg by 2 cos theta we can write here. So that is the tension at that points A and B. And now let us see how to find the tension at point C. That's the midpoint. The midpoint or the lowest point. That point C is here. And so to find the tension at that point C, I am taking the free body diagram of only this part here. AB, AC part or the CB part you may consider here. That when the C is the lowest point there. So now I am taking that FBD of that part here. So this is FBD of AC. So then FBD of AC means you may consider like this. This is the point C here and this is the point A. And as we mentioned already, this tension at this point will be along this direction, which makes an angle theta with this vertical. So with this vertical it is making an angle theta here. And now what about this tension at point C here? The tension at point C is the tension at C we are taking as the lowest point. So at the lowest point, as I said, the tension is always along the tangential direction. So lowest point means definitely it should be the tangent drawn to the string must be horizontal. So that point is nothing but our lowest point here. And so the tension at point C must be along this horizontal direction here. So it is along this horizontal direction. That is the tension at point C here. Is it clear? So C is our lowest point. So tension at the lowest point is along this horizontal direction. So that is nothing but our horizontal direction we are taking here. Is there another other forces acting on the string here? What is the other force? Weight of the string. So then weight of only this half of the string, because we consider only this half of the string here. So weight of this half of the string will be somewhere here at the center. Now it will be, I can write directly as mg by 2. Right? That is the other force acting in that acting on the string here, which is not required for us. Right? So that means in vertical direction you can neglect that, it is not required for us. So but actually you need to represent like mg by 2 is acting in vertically downward direction. Now let us take the equilibrium in horizontal direction. So that in horizontal direction I can write this as this component is T cos theta here and this is T sin theta. Now if you are considering the equilibrium along horizontal, so then along horizontal, along x-axis, I can write this as Tc must be equal to T sin theta. So the tension in horizontal direction, this side Tc force will be there and this side T sin theta is there. Therefore, the tension at this point should be equal to T sin theta. And the T sin theta value you can, that means T value you can calculate, we can substitute by using this equation here. So, this is nothing but our T value, mg by 2 cos theta. So, I can write this as Tc is equal to mg by 2 cos theta into sin theta. Therefore, the tension at that point 2 will be equal to mg by 2 into tan theta we can write here. And here don't blindly answer this, if such a question is there in the examination, blindly answer, don't remember this answer and don't answer that question in the examination, because if theta is taken with the horizontal, then you will get the different answer here. There we are taking that theta with the vertical. So for this we are getting this tan theta. If you are taking, for example, theta with the horizontal is given in the examination, then you will get cot theta there. So don't answer that directly there. So observe this theta value carefully there. So that is another example based on the string having that mass, right? So now let us see some other problems based on these blocks connected by the strings here. After that I will explain that pulley problems. And so now let us take one problem like this. I am giving a problem like based on this system blocks connected by the strings. Let us take this as 2 kg block and this is 4 kg block, and here I am applying in force of say 120 newtons. Right, so that is the force applied at that. That means those two blocks are connected by this string. That is a light string only. That means if nothing is given, as I said, we need to consider it as a light string, ideal string. If it is having some mass, they will mention that. They will give the string is having that mass, or they will mention it as a uniform string, uniform rope or uniform string. So now write that the system shown in figure is pulled vertically. The system shown in figure is pulled vertically with a force of 120 newtons. With a force of 120 newtons. Find acceleration of the system. Find acceleration of the system, and also find tension in the string. Tension in the string. That means tension in the string means string is here between these two blocks here. So tension in the string we need to calculate. And can you say directly how to write the acceleration here, acceleration of the system directly? How to write acceleration of the system directly? By using like our net force by total mass in motion. Net accelerating force by total mass in motion in that method. And now simply let us see here. Let us take the first free body diagram of 4 kg block and 2 kg block, and then let us solve, and after that I will explain this direct method here. So now I am taking this FBD of 4 kg. So 4 kg block if I consider, so this is tension is there, applied force is there in upward direction, which is 120 newtons. And this tension in the string will be there in downward direction. And is there any other force? Weight. Weight is there in downward direction. So under the action of these three forces, there is no normal reaction here, because the blocks are not in contact with any surface. They are in air. We are pulling them. So just they are connected. Because of that connection, that connecting force will be there, tension. And so now under the action of these forces, this 4 kg block is rising up with an acceleration say A. Now we can write the force equation for this. So that force equation we can write is the system is rising in upward direction. So definitely what we can write is the upward force is greater than this downward force here. So therefore this net force equation what we can write here is net force is equal to 120 minus 40 minus T is equal to 4A. Right, or otherwise I can simplify this as 80 minus T is equal to 4 into A. Let's suppose this is our equation 1. And next let us write the equation free body diagram for this block 2. So FBD of 2 kg block. So FBD of 2 kg block, similarly if I consider here, can you say what are the forces acting on this 2 kg block? So one force is, I can represent weight of this block here. Then what is the upward force? The upward force is only tension. You should not represent this 120 newtons here. 120 newtons is not directly applied on this 2 kg block here, but its effect will be there through this tension. So the tension is the pulling force for this block here. Is there any other force? So there is no any other force here, right? So that means again there is no any normal reaction here, because this 2 kg block is not in contact with any other surfaces, and so that this tension will be there in upward direction like this. And now under the action of these forces, now this is accelerating with acceleration A. And now again the acceleration of these two blocks will be same, because those are connected by an inextensible string, so that the acceleration of those two blocks must be same. And so I can write this as T minus 20 is equal to 2 into A. So this is equation 2, let us consider here. So just let us solve these two questions, then those two equations, then you will get acceleration and tension. So now I am writing this equation as equation 1 plus equation 2. Just let us add those two equations. Then I can write this as 80 minus 20 is equal to 2A plus 4A. So the T will be cancelled, right? This here minus T is there and here plus T is there. So 80 minus 20. So therefore it is A is equal to 60 by 6. So that you will get this value as 10 meter per second square, right? So that is the acceleration of that system. And here if you observe this final equation carefully, this 80 means I can write that 80 as 120 minus 40, right? So 120 minus 40 minus 20 by this total mass we are writing here. So that is nothing but our direct formula for that acceleration. Observe that equation directly. This actually, from this what we are writing here is A is equal to this 80 means 120 minus 40, this step. So 120 minus 40, and here this is minus 20 by this total mass 6 will be there. So now this is nothing but our direct formula for this acceleration. So that means our direct formula for this acceleration is, still we can apply this as F net by total mass in motion. So this formula still we can apply, but the simply thing you need to remember is, when the body is in our previous problems, the body is moving on the horizontal surface. When the body is moving on the horizontal, smooth horizontal surface, there is no role of its weight in its motion. That means no need of considering its weight in its motion, right? It doesn't affect the motion of the object. But when the system is moving vertically like this, here the system is moving vertically. When the system is moving vertically, definitely weight also will place a role, important role in its motion here, because the force is applied force is acting vertically upwards, weight is acting downwards. So what is the role now, weight of that weight role here? Weight is opposing the motion of this object here, right? That 120 newtons is trying to pull the system in upward direction, but weight of those two blocks, weight of 4 kg block and weight of this 2 kg block is opposing the motion. So now net accelerating force is nothing but, so here that net accelerating force is nothing but 120 minus of 2g plus 4g we need to write here, by this total mass in motion. Total mass in motion is nothing but 2 plus 4. So is it clear? So now this is nothing but 120 minus this is 60. So 60 by 60 you will get, so which is 10 meter per second square, which is nothing but what we are getting here. So either you can solve by using like this, or by using like our previously we mentioned the accelerations directly. Now also you can write that acceleration directly. Just you need to remember this term here. Weight is opposing the motion. When the system is pulled in upward direction, now the weight is opposing that motion here. So that net accelerating force means applied force minus that opposing force we need to consider here. So the opposing force here is total weight of the system. Both the weights are opposing the motion. So both the weights we need to consider there. So that is a direct method for this acceleration. And next here they are asking actually this tension here. So the tension I can calculate by using this substituting either in equation 1 or equation 2. So from equation 2 I am writing here. From equation 2 this tension is equal to 20 plus 2 into A is 10, so which is 40 newtons here. So that is the tension in the string. So this is the direct method here. So direct method to write this acceleration of the system, right? So that is our problem when the system is moving in vertical direction. So in the vertical direction, when the system is moving in vertical direction, you should not forget about the weight. Weight will plays an important role in the motion of the object when the object is moving vertically. And now let us take the same problem by having that string having that mass also. So now let us see that problem now. So now I am taking this mass of the string here. I am considering the mass of the string here. So this is 4 kg and this is 2 kg block, and this rope is, this is a uniform rope, let us consider. It is having this mass of 1 kg. The mass of that rope is 1 kg, and I am giving the points here A, and this is point B, and this C is the midpoint here, that's C, right? So now here it is pulled with a force of say 140 newtons here. So that system is pulled with a force of 140 newtons. Same question, we need to find acceleration, but tensions at A, B, C we need to calculate. Tension at point A, tension at point B, and tension at point C we need to calculate. So write that as shown in the system, as shown in the figure, as shown in the figure. The blocks A and B, sorry, the blocks 4 kg and 2 kg, the blocks 4 kg and 2 kg are connected by a string of mass 1 kg, by a string of mass 1 kg. The total system is pulled in upward direction. The total system is pulled in upward direction by a force of 140 newtons. 140 newtons. Find acceleration of the system and tension at the points A, B, C. Tension at the points A, B, C. And C, at the C you may mention that C is the midpoint. C is the midpoint of the string. So is it clear? Now I am going to write the acceleration by using our direct method here. So now the acceleration is nothing but net force by net pulling force by, or net accelerating force by total mass in motion. This is net, means net accelerating force we need to write here. Net accelerating force by total mass in motion. So then this value we can write this as net pulling force is 140 newtons. Now can you say what is the opposing force? So like that there is some opposing force is there here. So opposing force means weight of this block plus weight of this block. In addition to those two weights, now weight of this rope also we need to consider, because rope is also having that mass. And so I can write this as 40 plus 20 plus 10. Is it clear? Weight of this block 40 and weight of this block 20 newtons and weight of this rope 10 by total mass in motion 4 plus 2 plus 1. And so now let us simplify this. This acceleration will be equal to 140 minus 70 by 7. So that you will get this acceleration as 10 meter per second square. So it is the acceleration of that system now, right? And so now once you get the acceleration of the system directly, now you can take the free body diagram of those blocks, and from that you can calculate this tension at the different points. You can calculate it easily. Just to take the free body diagram. Now I am taking this FBD of, for example, let us take FBD of 2 kg block. Then you will get this tension at B easily. So now I am taking this FBD of 2 kg. So if you take the FBD of this 2 kg block, so can you say that what are the forces acting on this 2 kg block here now? The 2 kg block is nothing but tension, that means 2g is weight of this block and tension at this point B here. And now it is accelerating with acceleration A, the acceleration of the system. So now we can write this as the equation. What I can write here is TB minus 20 is equal to 2 into A. That A value is we already mentioned there. A value we calculated, that is 10. So net force equation, this net force for that block, net force is equal to MA. So net force is T minus 20. Therefore this TB is equal to 40 newtons you will get here. So that is the tension at that point B. So tension at point B is nothing but 40 newtons you will get here. Next, similarly, let us take this point block, 4 kg block let us take. Then you will get this tension at point A. So now I am taking this FBD of 4 kg. So FBD of 4 kg. So if you take FBD of 4 kg, then what are the forces acting there? So this applied force, that applied force is 140 newtons, and this weight of this block 40 newtons or 4g, but this system is accelerating, that the block is accelerating in upward direction there with acceleration A. Now again you can write the force equation here. Therefore this net force equation is for this block is nothing but 140 minus 40 is equal to 4A. Sorry. Here one more force is there, that is nothing but our tension required value. So tension at this point will be TA will be there in downward direction, right? So just again you need to remember to decide the direction of tension. Tension is a pulling force. That is a string only, what I said. So string only can pull the objects. So that string will pull the 4 kg block in downward direction here. So that this equation will be, you can write this as so 40 minus TA minus 40 is equal to 4 into A. And therefore I can write this equation as T is equal to, or TA is equal to 140 minus 80, because here this also 40 you will get. So then after simplifying you will get this value as 60 newtons. So that is the tension at point A. So now similarly you can calculate the tension at point C. So to find the tension at point C, so I am taking this FBD of AC part I am taking here. So here to find the tension at point C, either FBD of AC you can consider, FBD of BC you can consider, or FBD of BC plus 2 kg you can consider, or FBD of AC plus 4 kg you can consider. Just that C must be one point here, one end point. It may be the top end or it may be the bottom end of that system what you are taking. So that C should be included in our system. So like that you can consider in any way. So now just I am taking that AC part because the tension at A is already calculated there. Now the free body diagram of this AC part is nothing but I can represent like this. So the free body diagram of this AC is equal to, this is the AC rope I am taking here. So for this tension at A will be there in upward direction TA, and tension at C will be there in downward direction, and here this 1g will be there, that means half g will be there here, weight, because the total mass is 1 kg is given, and now the weight of this half part will be half kg, so half into g. Under the action of these forces, this is accelerating in upward direction here, that part is also moving in upward direction. So again you can write the force equation for this. So the force equation for this is TA minus the downward force, TC minus G by 2 is equal to 1 by 2 into A. So the force equation, just we are writing the force equation here. Therefore, this Tc is equal to TA value is 60 minus 10 by 2 minus 10 by 2. That means Tc is equal to, I am writing here, this TA value we already calculated 60, this is G by 2, 10 by 2, and this is A value is also 10 we are getting here, so 10 by minus 10 by 2 you will get. And so on simplifying you can write this as Tc is equal to 50 newtons here. So it is the tension at point C. So tension at point C is 50 and tension at point A is 60 and tension at point B is 40. And then tension, that means the acceleration of the system we calculated this. So like that you can calculate that. Now we can observe that if the string is having that mass, the tension is different at different points there. At different points we are getting the different tensions there, right? So that is the case where some simple examples based on the string having some mass. So then in our next class I will introduce about the pulley and I will discuss the problems based on that pulley. So now except that pulley problems, now we can solve the remaining problems here, that string having that mass also, right? So practice those problems based on this. Thank you.